At the end of lecture, I assigned what I thought was kind of an interesting problem, that we're interested in using an underground reservoir that exists at a constant temperature of about 15 degrees Celsius to help to cool our houses in the summer and to heat our houses in the wintertime and to hold it at a constant temperature of 25 degrees. And we're asked in this problem to calculate our monthly electric bill for a summer and winter month if, given some average cooling requirement, right, in the summer and heating requirement in the wintertime. Now, before I directly go about solving this problem, I want to bring in a little extra information that we probably need to start thinking about how to even look at this, because there, quite frankly, are two ways to run a Carnot heat pump. And the first one is that you're going to use as the other reservoir outdoor air. And outdoor air has an interesting condition where in the summertime, that the temperature outside is greater than the temperature that you want inside. And in the wintertime, the opposite is true, that the temperature inside is greater than the temperature that you want outside, okay? And in the second case, where we have an underground reservoir, that if we want the house to be at constant temperature, the relationship between the inside and the outside temperature is always the same. And really what I mean by that is, let's say that for the underground reservoir, you might have that the temperature inside is always greater than the temperature of the reservoir. And that's exactly the case in this problem. You also could have it where instead of a cool reservoir, you could have something like an underground spring where it's very, very warm, where actually the temperature that you prefer inside is less than the temperature of your reservoir. Okay. And so let's just have a look at these two cases really quick, and then I'll actually solve the problem. So let's do case one, where we have outdoor air. And let's just think about what it, or how it operates for a second, right? So in order for outdoor air to really function as a heat pump, it has to be able to do certain things. And in the summertime, essentially what is happening is that we want to take heat into the system at T cold, right? So we are accepting heat at the lowest temperature, right, from inside the house. And we are rejecting heat at the hot temperature, right? We're rejecting the heat to the outside. And in the wintertime, if you think about this, that the temperature outside is colder than the temperature inside, right? So let's draw that distinction here. In the summer, T outside is greater than T inside. In the winter, T inside is greater than T outside. So what happens then in the wintertime is that we're going to accept heat again at the colder temperature, right? We want to pump heat from the outside to the inside, right? We have to, if you're inside a house, you have to be able to accept heat, or the heat lost by the system or rejected by the system is inside. So again, we are going to accept heat at the outside temperature, which is T cold, and we are going to reject heat into the space at T hot. And both of these configurations are exactly what refrigerators do, right? They're both run as a refrigeration cycle. Now, there's some plumbing that has to be done because the order of compression and expansion is going to change. But these are both refrigeration steps, and we have to keep that in mind as we're solving, if we were to solve problems related to using outdoor air. Now, in the second system that I talked about, right, which we called, maybe we'll call it case 2, we're going to solve this with a constant or a reservoir at a constant temperature. That's lower than the temperature that you want inside your house, okay? And when this is the case, let's just draw this for a second. Of course, I'm not particularly great at doing that, but let's do that and think about what we want. Well, in the wintertime, right? So let's say that, here's the ground here, and we have our house. And really what's happening in the wintertime, that we have heat that I'll just call Q star that's leaving the house. And so if we have our unit here and it's connected to the ground, what we really need to be able to do then is have heat that is rejected at the higher temperature, which in our problem is going to be 25 degrees C. And we're going to take in heat at the colder temperature. And then, of course, we don't draw them explicitly in the process, but we have the other 2 steps in the Carnot process where we would actually do work, right, as well. Where these are the isothermal steps, right? And then these 2 are the reversible adiabatic steps. And so if you look at this, what's happening in the wintertime is that we are rejecting heat at T hot and accepting heat at T cold, okay? And if you look at this, this is exactly what a refrigerator does, just like we talked about a minute ago, right? So we are definitely operating on a refrigeration-like cycle in the wintertime when the reservoir below you is at a temperature below the temperature that you want. It turns out if the opposite were true and the reservoir below you were hotter, you would run a Carnot heat engine in the wintertime. Now, what does this mean in the summer? And we'll do the exact same thing and think about this for a second. So if we have our same house and the same unit, what is it that's actually happening in the summertime? Well, in the summer, you actually constantly have heat that's entering the house, right? And we're going to call that Q star. And the thing that we need to do here in our system is we need to remove the same amount of heat, right? So we have actually Qn, which is equal to this QW star, and then we have heat that is being rejected at the lower temperature. And so in the summertime, we want to reject heat at T cold and accept heat at T hot. And if we think about that, that is exactly what a heat engine does, or what the Carnot engine would do, okay? And so when we go about trying to solve the problem here, where we have a heating load and a cooling load given this underground reservoir, we have to think about, well, in the summertime or the wintertime, are we running a heat pump or are we running an engine, right? Or are we running a refrigerator or are we running an engine? And so if we go back to this problem, right, let's do this calculation again, right? So in the wintertime, because we know we're running a refrigeration cycle, well, we're going to think about this in terms of the coefficient of performance, which of course is the amount of heat that you can take in divided by the net amount of work, right? So we know that that is equal to Q in over the net amount of work that you need to do. And in our previous lecture, we derived an expression for the coefficient of performance for a Carnot refrigerator, and that was equal to the cold temperature divided by the difference between the hot temperature and the cold temperature. And so here we know that the cold temperature is 15 degrees C, right? Or the cold reservoir is at 15 degrees C. So that's 288.15 Kelvin divided by then 298.15, right? Because the hot temperature is the room temperature, then divided by 288.15 Kelvin. So our coefficient of performance then is equal to 28.8. And as we talked about in the last lecture, of course, that's to be expected that the coefficient of performance is greater than 1. Now, 28.8 is very high and artificially high. But then again, the Carnot refrigerator is the best that we could ever do. And so now to solve this problem, we're asked to find the amount of work. And so from our equation above here, we know that the amount of work that we're going to have to provide to the system is just equal to the cooling load divided by the coefficient of performance. And we're told that the cooling load is 40 kilowatts. And we just calculated the coefficient of performance was 28.8. And so that equals 1.39 kilowatts. And so the last thing that we can do here to solve this problem is to calculate the cost of running this for a month. And so, of course, our cost is going to be equal to the amount of energy that we need. And of course, we're assuming that Q is, at a constant rate here. So this is 1.39 kilowatts. Then we know that we buy electricity in kilowatt hours. So we're going to get that in terms of hours. So we know that there's 24 hours in a day. And that we're going to assume that we're buying the electricity at 11 cents per kilowatt hour. And if you cross out the units, you get to a cost of $3.66 per day. Or if your month had 30 days, that would be something like $110 per month. Okay. And there's our cost to run the refrigerator. Now, what about in the summertime? We said we're going to run this as a heat engine. So let's calculate the efficiency of such an engine, right? 1 minus T cold over T hot. So that's 1 minus 288.15 over 298.15. And the efficiency then is equal to 0.0335, or a little less than 3.5%. And now let's think for just a minute about what the efficiency means. It's the ability to turn the heat that's given into the system into work, right? Because we know that the efficiency is equal to minus the net amount of work that's done divided by the heat that comes into the system. Well, that means that the net amount of work done should be equal to the efficiency or minus the efficiency, times the amount of heat that is taken into the process. And in the summertime, right, Q in is our air conditioning load. And so that means that the net amount of work that's done in this particular problem is 0.0335 minus 0.0335 times Q in. And we were told that the cooling load is 50 kilowatts. And so that means that the net amount of work that can be produced by this process is minus 1.68 kilowatts. And you might think, wait a minute, that's negative. That means that net we're generating work. And that is true, right? We are running an engine. And the whole point of an engine is to generate energy. And so does that mean that running this engine in the summertime would be free? And the answer to that is not exactly. And it's because in the Carnot cycle, we often think about it as being a simple representation of the TS diagram where we know that we exist between T hot and T cold. And as we've labeled these steps in our class, right, we're going around clockwise in this diagram. And we like to label it very simply as Q in, Q out, W out, and W in. But that, quite frankly, is a little bit oversimplified because steps 2 and 4 are isothermal. And if you think about this as a closed system, as an approximation, well, for step 2, that would mean that delta U is equal to Q in plus just something that we'll call W prime. And if it's isothermal for an ideal gas in the process, that would mean that the change in the internal energy is 0. And even if it wasn't an ideal gas, of course, the change in the internal energy would be small. And so that actually means that Q in is equal to minus this W prime. And the same thing happens down here, where we actually could, for that particular step, do the same thing. And we know that Q out would be equal to minus some other value for the work that has to be done in that step. So actually, if we think about what's happening in the Carnot process, well, Q in is positive, so Q out is negative. So you actually get energy out or work out in steps 2 and step 3, and then you have to provide energy to the process or do work in steps 1 and steps 4. And that's actually the reason why when we look at something like the Carnot cycle, we always work with the net amount of work that's done. Because remember, it's a theoretical construct that we can't actually replicate physically. So this idea of what work in really would be for a Carnot cycle is somewhat abstract. And so we're not actually able, with the information we're given in the problem, to say anything other than the net amount of work produced is negative. And so if you were to tell me that that meant that running this Carnot engine is free, I would accept that in the context of what we've talked about so far. But if we really thought about this in its theoretical construct, we would insert work here. And if it were electrical, that would be fine. And we might not be able to utilize the work. So this might be wasted. So you might actually think of the work in as being the sum of those two, which, if that were the case, that would be an extremely large value, because remember, Q out, because the efficiency of this process is so low, is going to be enormous, because most of the energy, or most of the 50 kilowatts, is not going to become the net work. It is just going to become Q out. So that's a little bit of food for thought as we continue to solve some of these problems. You'll also see that as we transition to more realistic refrigeration cycles and more realistic engines, it's much easier for us to think about where we would provide the energy because it's in a real unit operation like a pump or a compressor that we know we're going to have to plug into the wall.